So Darko is a co-founder of causaLens with a mission to develop machines that truly understand cause and effect. He's got a PhD in computer science from Southampton in vision and machine learning. He's a trading system developer and also has been a research engineer at the National Physical Lab in the UK. And his talk today is about why causal AI is the only path to true AI. Over to you, Darko.
Thank you so much, and thank you for that kind introduction. Thank you, everybody, for finding the time to listen to me. Hopefully, I tell you some fun stuff, some interesting stuff. So today, we will talk about why machine learning is broken, especially in the context of financial time series data. Why current machine learning methodologies cannot really tell us anything beyond what has happened in the past. We will reveal a new science that is attempting to solve some of the shortfalls, and we will also present some real-world use cases from finance and beyond, where we've applied this new science and how we've been able to get amazing results. So before we go into why machine learning is broken, let's first celebrate some of the achievements that machine learning has had. If you have a problem that looks like this, cats versus dogs, or recognizing a cat in an image, machine learning does a great job. As long as you have the largest data set of cats and you have some processing power, you will have a beautiful algorithm. Is going to work with more than 99% accuracy. Machine learning is doing a great job there. We all got really excited when a machine managed to win against the world champion at the game of Go. And we were all excited, including myself, and that was a great achievement. Now, what cats and the game of Go have in common is that they are both examples of static systems. A cat always looks like a cat. The game of Go always looks like the game of Go. It has certain legal moves, the board is fixed, there's white, black pieces, that's it, right? Imagine now, you've trained your deep neural network to recognize pictures of cats and pictures of dogs, and all of a sudden, I present this algorithm with an image of a cat dog. And the machine will have no idea what to do with it. It will say, oh yeah, there's a cat and a dog in the image, or it will say, oh, I'm a bit confused. To us humans, we can look at that, and without having seen even one training sample, we know exactly what it is, right? And the real world is more like a cat-dog scenario at scale. So what has happened in the past in the global economy has nothing to do with what will happen next, especially when a pandemic hits. The past data becomes irrelevant, and therefore machine learning approaches do not know what to do because they all rely on past data. Current machine learning approaches are like driving forwards by looking at the rear view mirror. They tell you everything about the past, but nothing really about the future. Going one level more technically, current machine learning approaches are basically curve fitting exercises. We look at the data, put a curve, and we hope that the future will repeat itself and our algorithm will continue to work. Unfortunately, we either underfit or overfit, and those are the examples: left underfit, right overfit. But we haven't really learned anything about it. Like, this data could be about ice cream sales, it could be a stock price, it could be, anything. And the machine has no idea what it's fitting. It's just putting a curve. And if this is a multi-dimensional space, well, then it's a hyperplane, but it's basically the same thing. So no matter how complex the techniques are, this is really what machine learning boils down to. And I find that a little bit sad because we have all this buzz, but really all it boils down to is just a bit of curve fitting. And here is a symptom of the problem, not the cause. I'll get to the cause in a one slide time, but this is the symptom why something is not quite right. Our human brain is able to do these wonderful things by consuming only 20 watts of energy. That's the equivalent of a light bulb. Contrast that to a deep neural network that emits more CO2 than a diesel vehicle in its lifetime in order to train. So as I said, this is not a cause, but this is one symptom of the problem. Something doesn't add up. A neural network, human brain, 20 watts, diesel vehicle, lifetime, human brain still better. And here is the reason. Here's the cause why machine learning is broken. And maybe this cat video will illustrate the point. If you watch this one more time, you'll see that it would appear like the cat is causing a motorbike accident, but as humans, we know full well that these two are very independent events, and they just happen to correlate at one point in time. But if we use any of the current machine learning methods, this is what they will learn. They will learn that cats cause motorbike accidents. In other words, all machine learning methods are fitting curve and learning past correlations. And in many cases, especially in finance, those correlations are spurious and therefore do not generalize in the real world. To go with what the statisticians would tell you in the first lecture at university, correlation does not imply causation. And that's what I want to point out here is how correlation-based machine learning, which is basically all of machine learning we have today, fails in the real world. Here is an example of someone losing $20 million a day using automated AI platform, supposedly, that is basically telling, making decisions based on spurious correlations. IBM Watson failed to understand the symptoms and that led to unsafe cancer recommendations. Amazon had a bias tool for screening because the model picked up spurious things from past data. There's more. I can talk about failures in machine learning all day long, but here's a few more. Here's Microsoft chatbot learning bad things and really having no understanding of the real world and just essentially going with what it has learned, spurious correlations from the past. If you thought computer vision is solved, I did tell you can recognize cats with 99% accuracy, but you throw a little bit of complexity in the image, and a machine may think that this is a pretzel as opposed to a mushroom, and machine may think this is a manhole as opposed to a dragonfly. So we have a problem, and the problem is very, very severe, especially in dynamic systems like financial time series. So what do we do? Well, as any good scientist, we sat down, took a step back, went back to the drawing board, and started working on new science. And this new science teaches machine for the first time to understand cause and effect. And this is a huge, necessary but not sufficient step towards true artificial intelligence. So we're not saying that this is enough to get us to artificial general intelligence. I kind of like the human brain, but we're saying that this is one of the necessary steps to get there. Because if you look at babies when they grow up, they grasp the concept of cause and effect in few days from their birth. Yet language and all the other things come in years or months later. So cause and effect is so deeply ingrained in our understanding of how the world works that machines have to be able to do it if they're going to be ever intelligent. Currently, we just fit curves, right? Not very intelligent. And here is why you should care about it. You should care about it because it produces models that generalize in the real world much better. to put a number to it, in production, on average, causal AI models do at 42% more accurate than cutting current state of the art. And this is not just one model that we found somehow by accident. This is a large number of models that we have running in production for our clients. And this is how much better they are. Now, before you get too excited, I want to point out that this is still a nascent science. It's a nascent science that has received a lot of attention from the academic community. In fact, it's one of the hottest topics right now at all of the top AI conferences. And if for good reason. We haven't been able to solve all of the problems that are there. There are many, as any new science, right? When you start with a new science, the first approaches are not going to be perfect. And currently, open source methodologies and academic attempts have severe limitations when applied to the real world. And that is where we come. We are building the largest causal AI lab in the world, and we are building methods that do not have some of the limitations that are in the open source community. And so here are some more reasons why you should care about causal AI. Well, first, as we showed, it produces a lot better models that generalize and work in the real world, especially when the regime shifts. So when the pandemic came, anyone that used traditional machine learning model realized that they broke and they did not adapt to the new environment, to the new regime. All of our customers were able to react weeks and months ahead of the competition. So that's reason number one. But I will outline another 4 reasons. So there will be 5 key reasons why you should care about this. The first one was better models in the real world that adapt faster. But then second is, it will allow you to bring human level information in a lot more meaningful way. So here I don't want to go too deep, but essentially current machine learning approaches, you can only choose features. You can just say, oh yeah, this feature matters and this one doesn't. And that is a very blunt instrument. We are missing out on experts' knowledge, which comes in a lot more complex form than just choosing features for our algorithm. So there's the second reason you should care about. You'll be able to bring your human knowledge in a lot more meaningful way. But there's more things you can do with causal AI. You can evaluate interventions, something that you could not do with machine learning. So let's imagine a scenario where you're the central bank, Bank of England, and you're thinking about decreasing interest rates. And you want to know what the impact of that will be on unemployment, let's say. Well, you could decrease the rates and wait and see what happens. But a better way would be to say, I want to use a causal model to simulate an intervention. And if you're trying to do this with a traditional machine learning model, you're breaking the integrity of the covariance matrix, the correlation matrix, to such a degree that any what if analysis is totally meaningless. And we can go through the science of this if you like, but it is meaningless to do what if scenarios with existing machine learning models. So you're missing out on thinking about the world in a much better way without actually having to wait for data to come. But you can go further with causal AI. You can let machines learn by imagining. If you just take a second to think about how do you learn, you don't actually have to see everything to learn from it. You can actually imagine a scenario, evaluate it in your head, and actually be wiser on the back of it. Now imagine if machines could do the same thing. They would no longer need millions of samples to learn. They'll be able to learn without any data. They'll be able to imagine, learn, and help us. They'll be able to paint a world or a business outcome that we may have never contemplated. And just to be clear here, this goes beyond simulations, and this goes beyond data generating processes with techniques like GAN or whatever your favorite technique is. So this is very different. This is all based on causal model. Now, enough theory. So we so far saw machine learning fails. We need new science. We outline a lot of benefits that go beyond predictions. But now let's do some real stuff, right? Imagine a world, and I think the previous speaker was mentioning how important being able to find the right data set, the right signals is for model building. And we agree with that. We also think that simpler models that have only the causal drivers at their heart is the way to go. But this is a very hard problem to solve. So sure, you can, as the last speaker said, you could go and ask a human, that's good. But imagine if you didn't have to do that, or you could do something in addition to doing that. And that would be to automatically search the world's data for causal drivers and understand what is driving your portfolio, your business, your whatever you're interested in. And if you try to do this with correlation-based machine learning, what you will find is you will have a lot of false positives. You will have, if you do this at scale, the bigger the scale is, the bigger the false positives are going to be, and you will be able, you won't be able to know what's real causal driver and what is a spurious correlation. Let us go and illustrate this to a real example. Imagine you wanted to predict the price of natural gas, and you had every single movement of every single ship globally, leaving every single port, knowing what they carry. Well, we did this experiment. We did have all of that data, and we wanted to understand automatically which ports drive the price of natural gas. And we did it two ways. First, traditional machine learning, correlation-based machine learning. And that gave us a very long list of potential drivers, and we built some models with it. And we repeated that experiment with Causal AI, and we found things like this. For example, Trinidad LNG export were a highly correlated feature, and Causal AI said, well, actually, that is just a spurious correlation. And just by doing that, for a few more examples, we were able to get models that were 34% better, more accurate in the real world, just because we were able to filter those spurious correlations at scale. We repeated this experiment with inflation. So we want to understand how can we automatically figure out what drives inflation. And we did a correlation-based approach with current state of the art, and we got 26 drivers. That was spurious, and models were terrible. We repeated the same experiment, and we found 4 key causal drivers. And if you're an economist and you read those drivers, they make full economic sense. I'm sure you guys have heard that machine learning is not very useful when you have small data. Well, that is not the case with Causal AI. With Causal AI, you can build models with virtually no data. Here is an example of predicting an interesting, this sort of thing, property yields using just quarterly data. And you can see the results are more than 2 times better using Causal AI. And this is actually a real example. Let's go a little bit beyond finance. Let's see how causaLens is helping to solve and contribute towards the sustainable development goals. We have goal 8, 9, and 11 there. This case was a client that is an air cargo carrier. They want to understand what from the macroeconomic environment is impacting their orders. And their biggest problem was, how can we make sure we're not flying planes half empty? How can we understand what is driving demand, and therefore we can make sure we have the right number of planes, so when we fly them, they're fully utilized. In this particular case, we were able to improve their loading factor by 5% by automatically understanding the causal drivers of their demand, which led to millions of tons of CO2 saved and of course, a huge improvement of the bottom line of our client. We got involved in clean energy, and this was really exciting. If you think what's the biggest problem with clean energy, well, that is that you produce, the sun shines at a time when we don't need it in the day, and it doesn't at night when we need it the most, when we shower and make dinner and things like that. And so people came up with batteries, but the biggest problem is, when do I store, when do I sell to the grid? And in this case, we were able to solve both problems. We were able to understand the demand on the grid. We were also able to understand the supply and the generation of the renewable energy sources. And we were able to then optimize in a perfect harmony when to store, when to sell. And this is how that looked practically. This is a time series example of demand in the UK national grid. We were able to improve it by 8% versus the cutting edge model. And this is because we're able to automatically figure out what is causal, what is correlated. We then went into healthcare and wanted to understand what is our highest value add during the pandemic. And we realized that being able to predict patient flows more accurately by taking into account what is happening in the external world, it can lead to 4% improvement on the total cost of healthcare, which is 8 billion in the UK alone. So if we were to deploy this across the entire health system, this is the saving we could have, right? We haven't managed to do it yet, but the proof of concept is incredibly encouraging. So causality, it is the way to unlock and fix what is wrong with the current machine learning techniques. And it works beautifully for dynamic systems. So if you're dealing with time series, it is your only way. There's no other way. If you use correlation-based machine learning, you're just learning the past, driving forward, looking at the rear view mirror. Here's a little present from me to you. If you, until today, didn't know what causality is all about, but you're inspired by what it can do for you, well, here's how do you get started. And this is really an exciting time to be alive, an exciting time to advance science. So we would like to invite everybody, that is scientifically minded to really, spend some time to read this and get into this. Well, I would like to thank you for your time, and I'll be super happy to answer any questions that you guys might have. Thank you so much for listening.
Okay, thank you. So I will invite people to ask questions, and if you don't want to raise your hand, just jump in. If no one, I'll open up the questions. Just as an academic, I'm interested in the foundations of the science, and I see from the references it is rooted in mathematics. Is that correct or not? Because there is another way of dealing with causality from the computational world, and that's in things like complex event processing and dealing with time using various techniques from temporal logic and real-time systems and things like that. So there's a whole body of work in that space. Yeah. And the way you presented things seems to be more from the mathematical world, but maybe I'm wrong. Maybe it's both computational and mathematical at the same time. So could you elaborate on that science, the nature of the science, and whether it's single disciplinary or multidisciplinary?
Yeah, I think it is a single discipline that is just coming out right now. So if we go back a few years ago, it would be very hard to find anyone that would even talk about this topic. For the first time, so every knowledge starts with a definition. So someone had to go and define what it means. What is a causal model, right? Mm-hmm. And Judea Pearl, who is one of our one of the people we admire a lot, published a book, The Book of Why, in 2018, where he formally defined causality, through his ladders of causality framework. And so for a model to be considered truly causal, it needs to satisfy all ladders of causality. And that's what we are all about. We are all about being able to build models that satisfy that definition. So that's our definition of causality. And I guess to answer your question more directly, well, yes, of course, there's a lot of maths, but of course, there's a lot of computation as well. But it is a single discipline that is very well defined by thought leaders like Judea Pearl.
Okay, thank you. Anyone wanting to ask any questions? I would ask another question related to one of the problems with machine learning is how to validate your models. So is there such a problem with the causality? For example, just a simple thing is when we say cause and effect, I mean, are we talking the cause within 1 minute, or is it 1 month, or is it 1 year? So there are many aspects related to validation that are context dependent. And how do you deal with this?
Right.
Question
So we solve this problem in a generic sense. So I don't think it matters whether we're talking about tick level, minute, bars, a year, a month. I think the process needs to remain robust across all of the time horizons. So I don't think the time horizons matter. When it comes to process, to model validation, we are big believers in automation, and there's no silver bullet for model validation. But there is a large number of steps that if you're methodical about and they're automated, then it will always do better than ad hoc approaches to model validation. So we're big believers in automation and doing it in a way that we have a large number of tick boxes. And if all of them are showing green, sure, the human can come in and do the last validation, but with causal models, actually, you can have the human step in before that as well, before the model is ready, which is not something you can do with current machine learning methods. So when it comes to explainability as well, causal AI offers the opportunity to validate models and explain models ex ante as opposed to ex post, which is very, very important and a huge difference between the approaches.
Somebody from the audience would like to see the slide with the suggested lectures. So I don't know if you're able to show it again.
Oh, yes. I'm sorry, I just closed the presentation, but I would absolutely reload it. So just give me a sec.
So this way, while we finish the Q&A, they have a chance to take some notes. Yeah. Okay.
You can see this, the reading, yeah?
Yeah, yeah.
Great.
Okay, anyone wants to jump in with a question? No.
Great. Well, I guess we can call it a day. If you guys want to learn more, feel free to reach out. Here is our website. You can find us on find myself on LinkedIn. Just reach out, say hello, and we can chat some more.
Okay, I think probably everybody's tired.
Yes.
So we will probably bring this event to a close. So I would like to just thank everyone, particularly the organizers. Mike did a superb job with organizing the event, and James and Annabelle and her team. So thank you all very much.